We're quite punctual today. Huh? It's nice. Awesome to see still so many that survived the coding tutorial. As noted by Tim, it's less than for the coding tutorial, which is unusual, I must admit, but maybe it's just this cold, gray Friday, although that has also been the case before, but you know, who knows. In any case, yeah, welcome back to the Kai lecture, to the term. Today we have our 7th session, actually. That's the final for part 1. So if you remember maybe from the first lecture where we motivated this course and just causality and all these things, we talked about how it's going to be divided in 2 parts, where in the first part we're going to talk about classical causality, pure causality if you want so. And then in the second part, we are actually going to give this thing here a reason, a meaning. So we are going to look at causality for and from the perspective where we target AI. And so today is going to be a bit of a different lecture in the sense that we are going to discuss different topics, not just one particular topic and different nuances within that topic. So it's going to be different topics, and they are going to be beyond Perl essentially. So not all of these are without traces of Perl. So he has had his fingers also in these ones, at least to some extent. But it's ideas which other scholars have then pushed to, capture important concepts that we care about, that we can reuse, for example, for AI, in the lens of, in the world of causality. And also, if there's some time, we'll also do some questions, thoughts, simply exchange ideas on everything essentially we have discussed so far, right? So discovery, identification, and so on. So today's lecture, really, we did dive into a bigger picture view again. We abstract a little bit. We see some of these alternative ways of viewing causality and how they still make sense to call them causality, right? To see that the world is not just black and white, it's more grayish, yeah? And then just, you know, talk a little bit about things we've learned so far. So yeah, the overview for today. So at least content-wise, we have 3 sections we want to cover. So it's 3 frameworks of causality, which are alternative to Perl. The first one is going to talk about a non-graphical view on causality. At this, we have actually hinted starting from the very first lecture. And actually, the way we have also introduced Perl was to ease up the discussion of this part. Then the section 2 is going to talk about time, because also from the very first session, we remember, you know, people who have maybe been trained in physics, they recall, hey, causality, that's time. Like, where's the time dimension, right? So we're going to talk about that. And then finally, I'm going to tell you what causality actually is. Yeah. So pun intended. I mean, again, there's different notions of causality, and one of them is called actual causality. But you're going to understand why. Let's first jump into section 1, which is a non-graphical view on causality. It's the rivaling framework actually of Perl by Neyman and Rubin, although it's not like they developed it in one go. It's like separate efforts, which then evolved into the system. That's why we call it that. And it's the system that is mostly used actually by econometricians and, you know, people coming from the statistical causality side of things. And they essentially do all the things we have done so far, but just without graphs. And you're going to see how they formalize it essentially. So let's start again with the motivation, with an example, as we always do. Question. I guess Dave also in the first lecture was asking this question, should I get a dog? And let's consider 2 scenarios. So in the first scenario, you're unhappy, pretty bad scenario. And a dog should now help you to become happy, right? And you ask the question, well, if you do, then, well, if you do become happy, did the dog actually cause it, right? But what if you were to become happy anyhow? In that latter case, you would actually conclude that, you know, the dog didn't play much of a role, right? Like you got a dog and that's maybe nice for itself, but it didn't make you happy. It didn't change your premise. In scenario 2, however, you only remain unhappy when you actually not get a dog, right? So the dog here obviously plays an important role, because if you get a dog, it's going to have an effect. Yeah? You already see I'm using the word effect, and why am I do so? Because that's causality, right? And this causality framework by Neyman Rubin, it's called the potential outcomes framework. And in both of these scenarios, we already use now this notion of potential outcome. And next, we are going to formalize it a little bit. So if Y is your outcome, for example, in our case, the happiness of of the person we are seeing. So in this case, U. Then y equals 1, it's just going to be binary, denotes being happy, and y equals 0 denotes being unhappy. And then this notation is going to be very familiar now, at least to some extent, because before we used this y given the u, right, the units, right, the particular exogenous instances to denote a counterfactual. Here, however, we actually put the thing we intervene upon, right? So in this case, the treatment T. So getting a dog or not getting a dog, again, binary. So this thing is called a potential outcome, and it's denoting the happiness you would observe if you were to get treatment little t, right? Which could be either getting a dog or not. And so if we look now back with this notation in scenario 1, then what we can write is that for all treatments, yt is always equal to 1 in the first scenario, right? Because you will always be happy no matter what. But in the second scenario, you will only be happy if, for that matter, I guess, if we start with a premise unhappy, then it actually should be 0. I can correct this. But the point is just that it's fixed to 1, independent of the treatment. And then in scenario 2, you see that only when we get the dog, right? So when t is equal to 1, then we are happy, right? So it adapts actually with the treatment. So our potential outcome of happiness is dependent on the treatment on the dog. Now, we also use the term units, oftentimes also simply individuals, but we prefer units because we usually talk about a population, so they might not just be individuals in the human sense, right? So we talk also about these individuals / units when we talk about potential outcomes, and we can actually build them into our notation. So this object is now different from the one before because this is now a specific individual. So in our previous example, this would be you now, right? So individual I would be you because you were measuring whether you become happy if you get a dog or not. And now what we were looking at when we said that in scenario 2, you become happy because you get a dog was essentially this quantity, the IT, the individual treatment effect. We denote it simply by this little tau I. And it's simply the difference between these two potential outcomes, right? So this one would denote the world in which you don't get a dog, and this one, the world where you get a dog, and now you simply measure the difference, right, in terms of happiness. And if there's a positive value coming out, then you can conclude that actually getting a dog, because that's the thing you changed, is making you happy. Typically, however, we only observe a population, right? So actually this YT, right? So in this context now, this YT is actually a whole set of individuals. It's actually a random variable over all the different YIT that can exist, right? All the different individuals, right? You might be happy after getting a dog, but maybe you are the next person is a dog hater, and they get really sick over having a dog, or maybe they're just having an allergy to dogs, right? And so they would be unhappy because of that, right? Because of the consequence of symptoms they would get. So that's kind of the formal setting. And as you can tell, it's very close to what we have seen so far, actually. But now we're going to dive a little bit deeper. So there's this fundamental problem. We saw this in the very first lecture by Dave, the fundamental problem of causal inference. And that problem is that we unfortunately never observe both of these, because we have a binary treatment in this case, right? Could be even worse. It could be, continuous even, yeah, uncountably infinite. But in this case, for the binary, we never observe both. You cannot, go back in time and not get a dog, or get a dog for the matter of fact, right? And getting a dog or getting rid of the dog afterwards is not the same thing, because it's a different instance. The other variables can influence in the meantime, right? Something changes. It's not the original copy, so to say. And as a consequence, you can never actually observe this tau I, which we define, right? So remember here, what you see above is just from scenario 2. You get a dog, you get happy. You don't get a dog, you're not happy. And this is really measured now here by these values, right? Because the potential outcomes, at least in scenario 2, we know that they should be 1 and 0. So it ends up being 1. It would be a causal effect, right? But unfortunately, we never observe both. So you can never estimate this. Also, just to point out, we use, potential outcomes, counterfactual. These terms we use exchangeably, right? A lot of times. And that's also the case here in potential outcomes terminology. Sometimes we call Pearl's framework the graphical framework, and then this framework the counterfactual framework, which is misleading because the graphical framework also talks about counterfactuals, right? So, and yeah, that's why it's better, I guess, to just opt for the potential outcomes. But you can imagine the potential outcomes to be counterfactuals. Why? because of this very nature of things, right? So if you observe, for example, this one, where you get a dog, you will never observe this one, right? And this one is counter to fact, right? It's counter to reality. So that's why it makes sense to call these POs counterfactuals in the first place. But we don't opt to using that because it would convolute with, the Perl stuff and everything. So we just stick to PO. Now we see there's a fundamental problem, but we have also seen from the past lectures, I mean, you guys know now, and you've also explored in the coding tutorial, that we can actually estimate causal effects, right? Like there's something we call causal identification. We make use of assumptions wherever we get them from, right? Whether we just believe in them or whether we are grounded somehow in data and discovered, say, the structure. We can do something, right? And so that means, although there's a fundamental problem, we are not hopeless. And so how do people in potential outcomes go about this? Well, let's first visualize things, right? So on the table here on the left, you simply see the treatment, the Y for different individuals, and the YIs. Here, the subscript is just dropped, right? Trying to get you also accustomed to the fact that, people are not as precise always. Here from context, it's clear, right? So you're looking at different individuals. So these are the YIs. Yeah? As you will note, Y will here in this case correspond always to the one YI that we observe, either the one where we get the dog or the one where we don't get the dog, right? So it's essentially just copied over. And then everything where we don't know, it's going to have a question mark, right? And that's the bigger picture. And obviously, because everywhere, every row that you look at, there's always at least one question mark up to the final column. That's why in the final column, you always have the question marks, right? Again, because you can never observe the counterfactual. So this is what we look at, right? But now we can ask, okay, what kind of assumptions do I essentially have to make this work, right? Like, can I work with this, right? Because if you look at this now, the fundamental problem becomes very apparent, but we can actually, make reasonable assumptions, at least we hope to think so, to overcome this issue. What people then do is go, for example, for the average treatment effect, right? We exploit the fact that we observe a group of the same variable, of the same instance. It's essentially a template, right? Which repeats itself. Obviously, it has noise coming from, all the different individuals, but by resorting to some kind of average, we can get at least some insights on, say, whether, generally getting dogs is better, right? It's similar to these things of, that we say like, okay, smoking causes some illness, right? That's what a doctor cares about, a physician, right? Because then, you can devise treatment, that is the cause, that could be the case, right? Even though you don't know necessarily that for that particular individual, that will be the case, right? So the average treatment effect is written very similarly to the tau I we saw before. We just drop the I, we just have tau, and it's going to be expectation we get, so essentially the average over the difference of those YIs, which we measure, right? Which we have from the previous table. Those essentially equate then to just this quantity. It's just like treating, essentially like collecting all those YIs in the random variable Y. And so you can have this equality. And now, again, to just bring this back home, question of causal inference. What assumptions are really necessary such that this tau can actually be computed? And more specifically, computed through associational difference, right? So here, we don't have a counterfactual. We don't have any intervention, any potential outcome. We just have the conditions. We just look at the group that got treatment and that they don't get treatment, right? What do we need to make this jump, right? Well, one of the things we could use, for example, is ignorability. There's many ways of calling this. What you'll also see a lot of times is exchangeability. Actually, they are not exactly the same because the intuition and the idea, the concepts behind them are a little bit different. But mathematically, they end up having the same effect for what we're trying to do here. So I'm going to go into ignorability here because I think it's very intuitive based on the table we have seen before. So if we ignore how people have ended up taking the treatment, getting a dog or not getting a dog, or taking an aspirin or not taking an aspirin to cure their headache, and we simply assume that it was random, then what you can actually do is ignore all the question marks in the previous table, right? Graphically now, if we think back in terms of Perl, this would be the same as cutting the arrow from the treatment to all the arrows incoming to the treatment, right? Coming from every other confounding factor. This is also what we saw last week in the coding tutorial, where we did the randomized control tile, essentially, right? That's what ignorability really gives you. And formally, we can write this condition as following, that the treatment is statistically independent of both potential outcomes, right? So that's really what we have to say. And so if we can ignore these things, it's pretty nice, actually, because now we can actually do what we know. We can do causal identification. So we can write the ATE now in terms of purely statistical quantities, right? So remember again, we have here the differences in expectation, or the expectation over the difference. And now you can write it in terms of conditional potential outcomes. So because you know that the potential outcomes are independent, adding them doesn't give you any information, right? So you have this equality. So you can just add this condition here on T1 and T0. But now the cool thing is, because you know they're independent, you can also just drop now the potential outcome here, since T equals 1 matches obviously to the potential outcome where treatment is going to be 1, and the same for 0, right? So you have these matching now, so you can just drop the potential outcome here. And you end up with a purely associational one. So we see that in potential outcomes, we really have the very same meaning as in Perl, that identifying means writing causal quantities like these ones, these potential outcomes, in terms of purely statistical ones. So if you remember, for example, do calculus, right? We had the do operator, or we had the y subscript x, right? These ones we try to get rid of and just write them purely in terms of these. And here we are just trying to get rid of this notation, right? The ones where we have the parentheses. It's the very same thing. Yeah.
So what these do we like? We're always comparing only two states of the value. So what do we do if we have multiple states and maybe the correlation isn't a linear function, or like the connection isn't a linear function? Can we model this?
Yes, we can model this, but I don't have any slides on this right now. So I guess I could prepare something additionally, but then again, focus was not on this, but we can do this. Even in the case where it's continuous, the form of this thing. I mean, this is a specific causal quantity, the AT, right? It will change, but you can do this. This is anyhow without loss of generality. When someone says without loss of generality, always be cautious, right? If you don't believe, go in there. Obviously, we're just doing binary for the sake of the concepts and the examples. Yeah, so we used ignorability. We were able to do causal identification. But now we are getting more deep into, the power of potential outcomes and specifying things in terms of, notation, in terms of algebra, right? So what we really want to have is realistic assumptions, right? So if you look at, econometricians, but also physicians, they, in my observed view so far, attending different conferences, workshops, and so on, they usually resort to potential outcomes, actually. And then they're trained very well in this whole framework. And what they like a lot about this framework, that you're very explicit about the assumptions, right? There's a very clean way of writing them down. And you have a lot of methods, like, for example, Morris was just asking, you can do categorical variables, you can do continuous variables, you can do multi-target interventions, all kinds of interesting things. Yeah. But all of them, what they seek is, going towards realistic assumptions. I mean, essentially, we Perlians also did this, right? But this is what we go for. So why was the previous assumption not really realistic? Well, see, we are now settling on a different assumption here, which we call conditional ignorability or conditional exchangeability. Yeah. And that is the same as no unobserved confounding. Again, there's a lot of terms, you can call this unconfoundedness, you can call this no hidden variables. There's different ways of calling this, right? Some might be better suited for a given context. But even then, this assumption is pretty restrictive, right? So you can imagine now, ignorability was even worse than that, actually. So you didn't even have any covariates you adjust for to get your causal identification, right? And here, this is the case with conditional ignorability. So we are just saying that we can find what we did previously with Perl, our adjustment set, for example, our parent sets, our confounders, and we can work with that. At least, we could, block the backdoor, right? That's essentially what we're trying to do here as well. And they call this the conditional exchangeability property, that we can find some factors X, which in this case would correspond to the adjustment set, for instance, which is less restrictive, right? Because you might have access to some variables which help you to do this, and you can still end up doing causal identification. Next, what I want to do then is just discuss some of these assumptions, right? Also, let you be the judge of whether you think they are realistic or not. So one very common assumption you do in potential outcomes is the one of positivity. So for all the observed covariates X, right? Again, covariates, we in machine learning call these features, right? In Perlian notation so far, we have just called them values, right? But essentially, these could be all kinds of things. Example, again, we have like, say, a confounded structure, a triangle. Essentially, there's treatment affecting the outcome, and then there's some variable which is affecting both our treatment and the outcome. Then that covariate could be, for example, the kidney stone size. If you remember the kidney stone example, we had patients with large kidney stones and small kidney stones. And obviously the ones with large kidney stones, they had more urgent needs, so they were treated differently. And so these could be any of these covariates. It could just mean, for example, someone has a large kidney stone. And now what you're just saying is that observing, this thing should be positive, right? So there are cases of people, having large kidney stones in your data. And then ultimately that the propensity also is positive, right? So the probability of getting treatment, given the fact that that someone has, for example, a large kidney stone, should also be non-zero. You have to have that assignment, right? Because otherwise these people would never get to treatment. So that's really the intuition, right? So you have a positivity violation within some subgroup of data, such that everyone always receives the treatment or not, right? So because if you would allow this to be zero, then the other one, because in this case it's binary, would be 1 minus 0, it would be 1, right? So you would have someone who always gets the treatment and some other group who never gets the treatment. So in this case, for example, the ones with large kidney stones would always get the treatment, for instance. Yeah. And this is very important, as you can imagine, because ultimately we are comparing groups. We are comparing them in a smart way so that we can conclude about the causal nature, about change, right? And if we don't have that, at least in my opinion, I think this is a fair assumption. Another common assumption is that of no interference. It looks way different now than the previous one, but let's look at it. It's very simple in the sense that it's just this equality. So you're saying that the potential outcome of some individual is just going to depend on that individual's treatment. That's what this Ti now means. So these T1 to Tn, they're not time series. They are the different treatments that our n individuals in the population get. And what you're just saying is that the treatment, the happiness, given some treatment of person I is just going to depend on their treatment and no one else, right? Here we could already start, discussing whether this is realistic. And I guess here it's already, less realistic, especially if we are saying a pandemic setting, right? Like, you getting a COVID vaccine, for instance, it's probably not going to satisfy this, right? Because of all kinds of other factors in which way, other people will influence your decision making. Yeah. To take the less harmful dog example, right? Even there, you might think, hey, my friends, we all have dogs now. Let's hang out together. Yeah, let's have fun. Let our dogs play, right? And this would also be violated in that case, right? But on the face value, it seems like a fairly, reasonable assumption in the sense of, things that we know in machine learning, like, Markovianity, where, we just depend on, I guess, the previous time step and nothing before. But again, like the previous one, you can be the judge, right? But we need some of those to make things work. Another common assumption is that of consistency. Again, this also looks different. It takes the form of this logical rule that if T is again the treatment, then the observed outcome Y is the potential outcome under the treatment T. So if the treatment that a person gets or should get is T, then that implies that actually the observed outcome, which is Y, matches the potential outcome, right? I think this is fair in the sense that you're just saying that, okay, if you give someone the treatment, the potential outcome of that person is going to be the thing you actually observe after they have gotten the treatment, right? So in terms of the table that we have seen before, it's really just saying, this property is just saying that you have these copies, right? That the y will correspond to the yt according to which t was chosen, right? And yeah, that's really intuition. Now, what you will encounter a lot if you maybe have a look more into this literature is this SUTVA assumption, right? Or SUTVA, well, the H stands for assumption, right? It's the stable unit treatment value assumption. It's really a combination of what we saw before, no interference, that no other treatments are affecting your treatment, and this consistency, that the potential outcome is the thing that you observe. Also, that, it's a deterministic function and so on. There's some minor technicalities, but that's really this SUTVA. And so these things, again, they give us causal identification. And I told you that they were common assumptions because actually these are really the standard assumption. They're like the bare minimum we have to make because these, question marks on the table are very troublesome. You can, erase them, fill them up, but that wouldn't mean anything. And here we now have, I call it now causal identification 2.0 because we have taken, more realistic assumptions. But naturally, the form now of our tau, which again is just the expectation over the difference of these potential outcomes, it's going to look a little bit different. Here you have a simple derivation in 4 steps, essentially. So by linearity of expectation, this is just what statistics probability theory gives us. We can just separate those. Then again, probability theory, law of iterated expectations. What you can do is you can put the condition on each of those quantities and then average them out, right? That's just the same thing. But now you can actually make use of these common assumptions that we have previously. So in the next step, we actually combine 2 assumptions at the same time, positivity and unconfoundedness. And what you get then is, pushing the treatment like we did before, the trick from before, into the conditions, right? Because again, conditional exchangeability, they're independent. And the positivity, because if you would actually write down what these terms mean specifically, you would see that otherwise you would divide by 0, and you cannot do this. So both of them are happening at the same time in this step. But you really just see this one. And then the final step is just consistency, right? That again, you're saying that the thing you observe is going to match, so we can drop the thing in the parentheses. And now you have written the tau in terms of purely statistical terms. And as you can see, the difference only now to before is we look again at the group which got the treatment and the one which didn't get the treatment, but we additionally look at different groups of X and average about over all of these groups. And then, the average over these differences within those groups of people who got the treatment and not actually gives you the causal effect. It actually tells you just this quantity, which ignores the axis. How does my treatment affect the population generally? And that's pretty cool. Now, the community generally, right? So actually earlier this year, there was again a workshop was organized in Eindhoven, where Dave is now professor. And it was a workshop essentially to let these 2 sub-communities talk, right? The graphical people and the counterfactual potential outcomes people, right? And you can tell that these people, they really don't do the things the same way, right? Like we really use graphs in the Pearlian sense, and these PO people, they don't use graph, they just stick to these formulas. And so, presentations can look very different. Some might argue that, PO presentations become very dry, right? But then again, some argue maybe that graphical presentations get bloated and are not as efficient, right? But really the message I want to put out here, at least this is my opinion, and I guess many people actually agree that at least I've talked to, it's really dependent on specific application, right? It's just 2 ways essentially of looking at the same thing or a very similar thing, almost same thing. But these 2 ways come with advantages and disadvantages for your specific application, right? It might make sense to think in terms of graphical models in a certain setting where you maybe need intuition about, this whole structure of the thing, maybe applying something like deseparation, whereas you can use potential outcomes, especially if you maybe in a medical setting, right? I mean, you see the treatment and all these words that we use to describe it are already developed within that framework. Generally, I put this equivalent here in quotations because as you will see next year, there is a unification approach. Yeah.
There's a potential outcome framework scalable to like those or variables or not?
No, I don't think so. But I guess partially also because of this nature, right? I would have to check myself now. I haven't seen, well, the works I've seen, I guess, this year. I mean, they can do some awesome stuff, but I've never seen anything which exceeds the Perlian stuff. Then again, well, they are kind of the same thing, although they're not, right? Like just write it differently, and there's some nuances, I guess. So it's not like what Christian had to say about partial identification, if you remember, was like, hey, we are writing this in linear programs. This is polynomial, but the problem is exponential, actually. Did we make a jump? No, we are not making any jump here now, right? But still, in specific applications, people make amazing progress, right? And then again, I guess, yeah, causality is really concerned with the questions of, you know, if I make these assumptions, what will be the sound conclusion? And less with scale, right? Which is, I guess, inherently a thing biased towards, you know, machine learning practitioners and people who are concerned with systems and yeah, stuff like that, networks. So yeah, let's see. Maybe if you find out something, you can tell us. But nothing which would surprise any of us. Yeah. So what I just wanted to say before the question was unification approach, which is called the single world intervention graph, is a framework which was proposed by Richardson and his collaborator at Harvard to unify, to express in one framework both of these frameworks. Because again, we felt like we were doing the same thing, and well, we kind of are, yeah? And I'm just going to briefly show you this framework. But why do I say that they're equivalent in quotations? Well, actually, at the very same workshop, there's a person I got to know, Patrick Klösel, who presented a work where he actually went back and asked the questions, well, what does it mean to be equivalent here, and to which extent are they? And he actually proposed different notions of equivalence, and it turns out on many of them they were different, right? But then again, nuanced versions. It would be something like maybe, you know, do they match maybe on all the theorems, on like all the key knowledge that we can extract from the framework, right? Or some other kind of ideas of comparing the two frameworks. I mean, evidently, the frameworks, you know, think differently, they write differently, so they are already different on that notation. But it's still interesting to observe whether we can actually make the bridge fully, because if we could make it, then the implications might be that, you know, people can just borrow ideas from these papers and vice versa, right? And that would be very helpful actually for the community. But yeah, just to give you now a little bit of an intuition, feel free to check it out, but as many of these things, it's a very long and dense paper. It's like over 100 pages, essentially a little book. And what they introduced there conceptually, I mean, amongst many other things, but the thing for the single world intervention graph was the node splitting operation. So a node splitting operation creates a swig, yeah, from a regular causal graph, as we know it in the Perlian sense, yeah, in which we split the intervened node, for example, X, say X is the treatment, and then relabel the outcome node as a potential outcome now. So you go from X and Y to this X being split. There's still the variable X, but there's also now this new node, which is X equals 0. And this one is the only one now pointing to not Y, but Y when treatment X is 0. And how does this work? Well, deseparation now on this swig actually will reveal you something like this, that X is actually deseparated, and then, you know, assuming faithfulness, statistically independent of Y, the potential outcome Y when X is 0. And again, if you remember these things, these are the assumptions we saw from before, right? The assumptions we make in potential outcomes to do causal inference. So what you did here now, or what they did here now, is take a causal graph in a Perlian sense, split it, make it a bit different, right? Such that if you apply, again, a Perlian framework, deseparation, you get up something in PO language, right? And really this work is the groundstone while, well, people think that it's equivalent, right? And I agree, I think it's just, you know, you got to choose what's most suitable for your application. But then again, we might be wrong. Let's see what happens with, you know, people like Patrick who might investigate this and just ask to which extent they might be. I would have to recall how much Richardson and his collaborator actually proved on this end. But it's a very interesting discussion. And it's very interesting also to see, you know, someone write in the abstract, like, or in the introduction that, you know, some of the claims that Pearl made were wrong, and we show this and everything. It's a bit different than you see the typical machine learning papers, and that's actually quite refreshing. So yeah, these are the single word intervention graphs. Just remember, they unify potential outcomes and Perlin causality. And as you can see, PO so far looks very close to what we have known from Perlin causality. And that's why I found this comic to be very nice. So it's the mathematical symbol fight. And what you can see here is now an axis pointing in two directions, with a bunch of mathematical symbols placed on this axis. And if we go to the right, they become more useful for a fight, right? A fight between people. And that's what you see below here, different people fighting with different symbols. And you can see the real numbers can only be used as a shield, right? Whereas I don't know what this notation is. It's just like a spear, right? But you can use the spear to, you know, pierce a person, yeah. I guess Rho is also pretty useful because you can just strangle someone, right? Or just, you know, pull them in. But yeah, I guess why I like this so much, especially in this context, is because it's just notation, right? Like I've argued with, and here my colleagues know, I've argued with people, and I've got papers rejected myself because my notation was wrong. I was asking, how can a notation be wrong, right? I mean, it's something I define, and then, you know, I try to use consistently. Sure, some notation might be more pleasant and useful in some case, right? But that doesn't mean it's wrong. And I guess that's the same thing we are playing here with potential outcomes and graphical models, right? Like the way I see it, it's really just people who are biased towards one or the other by, you know, the development they took, right? The education they took, the treatment they got, essentially, right? So I know people who have never read the Book of Why, and they have started with, Neyman Rubin and these things, right? Because they studied, for example, economics, switched to, you know, econometrics topics. And then there's other people, for example, like me, I actually started with the Book of Why, right? And so I ended up with Pearl, right? But I at least try not to conclude anything about the other side or something. I think we're all causality researchers, and that's the whole point. And use whatever mathematical notation you want, right? Just be consistent, yeah? So maybe take this opportunity before we move on to a completely different train of thoughts. Any other questions or thoughts, impressions you have over potential outcomes and mathematical notation? Yeah.
Like other general recommendations to decide for one other framework.
I think there's actually a work on this. I think there's actually, or maybe I'm confusing it with something else, but I remember there was some work, I believe, in causality where you had like a guide, essentially, like asking questions, or do you care about this or that? And then, you know, and I think it actually was on potential outcomes and kind of and Pearl, but I'm actually not sure. I would have to check as well. But yeah, it's a good question. I mean, it's a good question. I guess your natural bias should be the one you're trained more in, simply, right? Because you feel more comfortable in it. Cool. If there's nothing else for the moment, then we'll just jump to section 2. What about time? I mentioned, you know, physics, right? Like time, causality, events must happen after the cause, right? Like the effects must happen after the cause. So we are just going to discuss now how we can express causal relationships over time. As you see, I put causal also in quotations because the famous framework by Granger, who actually also won the Nobel Prize in economics back then for his work, is not causal in the sense that we would talk about it, right? At least we cannot justify it, yeah? But then again, it still has some value, and it's actually probably the most popular framework to this day for time series modeling in causal kind of settings. So let's discuss this in more detail. So just a general problem now. We have talked about causal reasoning, right? And now we want to involve time. Actually, you might think this is a hot take, but actually just on the problem side of things, conceptually, reasoning about causal relations amongst variables which have some kind of time knowledge is easier than causal reasoning without time structure. Why? Because causal structures must obey time. Yeah? That's the conceptual reason. Well, if you would now visit a group like Moritz and I did, for example, Professor Runge's group at TU Berlin, I mean, they are just the best when it comes to, causal modeling or time series. They would tell you, well, it's the opposite, right? It's super difficult. And yeah, that's true. Why? Because we actually immediately violate the standard IID setting, right? Remember, IID, identically independent and identically distributed, right? Like you could maybe argue on the identically distributed part that maybe, the mechanism and stuff like this stays the same, but even that could change over time, right? But definitely the independent is violated if, my next random variable is, the time step evolved before the, after the first one, right? So that's already non-IID. But all of the methods that we developed so far, at least, in an estimation sense, they are IID, right? So we would have no guarantees. Like we can apply them, we can see what comes out, right? But there's no way of trusting them. And so easy only on the surface, essentially. It's actually difficult. It's very difficult. And again, there's whole labs which just dedicate to this topic. So let's talk about SCMs now. Now we go back to Perl and everything we know and love and whatnot. And we are going to have random variables now, collections of random variables, stochastic processes. Yeah. It's not important to know many, mathematical details about these ones now. We didn't introduce them back in lecture 2, right? This is just, again, it's, giving you some intuition. If you can work with these things, that's awesome, right? It's more that you can learn, right? But essentially what we just need is, these different processes. We measure them over the integers in time steps. And we always look at a window of, at most Q values. Conceptually, they can be infinite, right? Counted be infinite in this case. But we always consider a window where, in this window, this is the only effects which could have, where it's sensible to call this actually a causal effect. And notation quickly becomes horrendous on these kinds of things. Why? Because, well, it just gets overloaded, but it's actually very simple, right? So again, we just have our variable like before. Note that just now, the specific variable that we talk about, x1, x2, x3, is now put in the superscript, right? In the subscript, now we put the time step. This is just some convention we adopt here, but this is just important to know, right? So this is some jth variable in the t time step. And its value is determined by a structural equation for variable j, right? So here, I mean, this function in this case is agnostic. The causal mechanism is agnostic. And it depends on some exogenous term. Again, just, there will be some exogenous terms for variable j, but just in time step t. That's a detail to notice. And then these PA here are the parents, right? But the parents across all the windows. So it's essentially all the variables in that window frame that somehow had an influence, right? That somehow, affected our variable xj in time step t. Yeah. So they can be delayed effects, right? Like they can be a variable, say 10 seconds ago, which influenced my decision now even, yeah? And that's really what this intuition gives you. And this is a perfectly fine SCM over time. Now, a popular choice of these SCMs would be something like a vector autoregressive model, VAR for short. And that's really a linear model, right? Where now the structural equation takes this form, right? So you notice, again, left-hand side looks the same, right-hand side now is a specific functional form, specific bias. And what you have here is simply the variable xt. So all the variables, which essentially, these are all the variables, right? Up to, window q with some learnable coefficients matrix, right? And this thing will tell you now which ones are the parents or not, right? Like this is the thing you optimize for. That's why this is not the parent set, but all the variables. But this thing will then, in combination, dictate which are the parents actually. So this will be the thing we saw earlier, and the sum makes sure that it's all these parents. And then we just have the separate noise term, right? In this case, actually, you use the ones from the previous time step. Yeah, so that's actually a popular model, which is used oftentimes. You see that, we generally often resort to linear models because, we can interpret them. They are simple to optimize. But then again, if our setting is nonlinear, which is virtually always the case, then, we get difficulties, we don't get guarantees. But especially even in time series, these things become very important to handle them. Now, I just want to talk a little bit about terminology. So we just saw the SEM defined over time. We saw one popular model being the vector autoregressive model. Now I want to talk about the graph, which is applied by such an SEM, or which is actually underlying such an SEM, which could be admitted. So it's going to be a causal graph, right? In the very same way that we looked at graphs before, where we have these nodes. And again, remember, so we just collect d different nodes over, time series over the integers, so it can be infinite. And one important thing, and that's the thing why we said originally conceptually easier, because we have this constraint that only previous time step can influence what is happening right now, right? So past always goes to the future. There's an error of time. It's not like past, the future can predict the past. The only, I guess, more interesting thing to that regard is when t is equal to s, then we have connections which are instantaneous, right? This could be modeling choices, right? Of course, switching on the light is not instantaneous, right? Like what is even instantaneous? But in all essence, it's instantaneous for anything practical we'll consider, right? Because of the short distances we have in comparison to the velocity, to the speed of light, right? And this thing that we just defined here essentially, so a graph with just these nodes, yeah, so we just have variables which now have this time step label, where we always go from past to future. This is called the full-time graph. And it's actually a DAG, or at least we assume it to be a DAG, but it's generally a DAG with infinitely many nodes. It's the first of its kind that we see like this. An example could be something like this. We have three different variables, x1, 2, 3, measured over here now 5 time steps. And we can see that there's no instantaneous effect. So anywhere you look, you will never find any column here, which will have rows in between. You will always also find, as we just discussed, arrows pointing from the past to the future. And in this case, what you'll see is that actually x3 only determines itself and x2 with the help of x1, right? So x1 is the only one which is completely autonomous here. And there's no outgoing edges going from x2 or x3 or x2 to x1. Now, instantaneous effects, again, they would look like something like this, right? You would have in the time step immediate causal influence on another variable. And it can be mixed, right? Like we just keep the one from before here. We just change, for example, this one on x3. There's no delay anymore. Yes?
Could you go one step back, please? Why do we decide to go from x1 to x3 2 time steps ahead? Why don't we say, oh, it's only one time step and then drop down and keep it down and stick back?
I don't know what this SCM is or what it represents. It's just an example. This is what is admitted by the mathematical structure we just defined, right? It could be, one time step. It could be 0 time steps, instantaneous, right? It could be 5 time steps. It could be none at all, right? This is just to highlight that it could be looking like this, could be looking like this, anything, right? Now, another important object is the summary graph. And now the summary graph is interesting in the sense that it resembles a lot more the things we have seen in the past, the classical causal graphs, right? In a sense, we can see all the graphs we've seen before as some kind of summary graph, right? Because we don't look at the variables considering time, but we abstract them away. Yeah? And we can actually construct the summary graph from the full-time graph. So we draw an edge from some variable j to k, whenever, j is unequal to k, of course. If there's really just any edge from the past pointing to that variable. That's the only condition, right? Like the effects could have stopped, but as long as something influenced that variable, we have to draw an arrow. At least that's how we define it here, to keep these causal semantics. To put it differently, if we just define this PS to be the past, then there's just one variable in the past which influenced our current variable we're looking at. And this thing then we call the S-graph, the summary graph. And the summary graph can actually contain cycles very easily. To give an example again with the previous example, if this was our full-time graph with instantaneous effects, then this would be the corresponding summary graph. Looks definitely a lot less complex than the previous one, right? But you can convince yourself that this is the abstraction of it, because x3 and x2 are really just, dictating themselves. And we're not denoting this by, a self-cycle, according to our definition. To, at least at this point, we avoid acyclicity. And then we see that x1 and x1 is affecting both x3 and x2. It's a fork, right? And so that's what you end up with. So even if in this part, maybe x1 would not have any influence anymore, because in the full-time graph, at some point it had, we draw this edge, right? Yeah.
Is the mapping in that sense that the summary graph, I guess it can have cycles now, right?
Yes, it can have cycles. Correct.
So
yeah.
over time steps, if variables influence each other.
Correct.
So is this, do we have to take special care when working with the summary graphs, or can we just see them as normal causal models, just that we admit cycles? You can see them as normal causal models, at least to this definition. This should be the case, yes. Whether you could have an alternate notion of a summary graph, maybe where this is not the case, I can imagine. But obviously, if you have cycles, then we automatically end up in a setting where, right, like we usually work with DAGs, and it's not a DAG anymore, and we get difficulties. Then again, Bongas, as you know, has helped us here. But yeah, that's the thing. Because this can easily happen, this already makes causal inference a lot more difficult, right? Okay, so now we actually want to talk about how we learn this thing. Like, how can we guess the structure, right? Like, how can we make a right educated guess, yeah? So let's consider just a bivariate time series, which just means that we have two variables, two time series essentially, right? One is called x, one is y. One is measuring some feature, one is measuring another. And we want to now discover whether x is the cause of y, right? Whether, this one series is predicting the other. Well, not predicting, it's actually causing the other. And there's two things we can actually conclude. So this is a theorem with structural causal models. Again, we are using SCMs here. That if there exists some time step, t, in our integers, where y in the current time step that we're looking at is dependent on x in the past, right? So any time step before t, given its own past, given the fact that we have, observed values, then the summary graph contains this arrow. Then the summary graph actually says, yes, x is a cause of y. So again, to just highlight the importance of this, so you have two time series. They are for an SEM. You look now, you're given, or you look now at y in the current time step, you're given all the previous time steps of y. So you condition on that information, and still x is helpful in predicting y. Still x changes your beliefs about y. Then you can say x is a cause of y. Now, if you assume some minor technicalities and that there's no instantaneous effects, if you have this property here, that essentially for all time steps, there's an independence. So x, the past of x is never helping you. Then you can for sure actually conclude that there's no connection, that x is not a cause of y. Again, remember, we're not talking about now the reverse direction. It's just x as xy now. But this is a fundamental theorem, I guess, for SEMs, looking at the bivariate case now, at just two variables, right? And why is this important? Because the thing that Granger developed, well, why is it so popular? How can we justify it when I said earlier, I mean, we have not seen yet what it is, but how can I say that, it's not really causal and so on? Well, because this is Granger causality. Granger causality is, or we say that x is a Granger cause of y, exactly then when x in the past variables of x, the past measurements of x, help in predicting the current measurement of y, although we know everything about y's past, right? That's really the intuition, right? X influence y whenever the past values of x help in predicting y from its own past. So if we test this condition and it's fulfilled, we say, it's Granger causality, right? If you are reading a paper
about Granger causality, what you'll oftentimes see is they'll mention Granger maybe once or twice, but because, people are lazy, they don't want to write Granger cause every time. They just say cause, right? So just going to talk even about causality because they expect you to know which framework it is, right? But this is not potential outcomes. This is not Perlin causality, and it doesn't match any of these achievements that we've had with, confounding, identification, interventions, and all these things. Actually, you see this footnote. Granger himself then later, after, winning the Nobel Prize, and, there was discussions and blah, 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 admitted to this and said that, Granger causality really just tests whether X is forecasting Y. Well, now, if you are paying close attention, you might just say, hey, but this condition just looks like this. And we know from SCMs that this works, right? Then again, here we place a couple of different assumptions, right? Which are missing here. Granger was essentially just claiming that if you do this, then you have causality, right? So we can get this to work, for example, for the bivariate, but then multivariate and so on and so forth, there's difficulties we face. And not just that, right? But before we look at some violations, I just want to give you some more intuition on the practice, right? So in practice, Granger causality usually just means, again, because, we look at vector autoregressive models or just linear models, means comparing two models. And the two models really that you compare is how you predict Y with and without X. That's it, right? Like if I assume, this linear function here, Y depends on its past, given some parameters and some noise. Here, I'm just saying it additionally depends on X. And these ones, they're the only ones assumed to be IID. So these stochastic processes for the noise terms. And really, we then always just conclude that X Granger cause Y whenever the variance of the noise term for the model that includes X is smaller, right? So again, you can just train these things. If you see X is significantly better, you say it's a Granger cause, right? But it's important to highlight that it's not a general cause or a cause in the Perlin sense or anything we have seen so far, because there can be hidden structures and much more. So these violations would be hidden variables, deterministic functions, mediators, and actually a couple of more things. And this is all independent of the fact that, there's no notion of interventions, there's no notion of counterfactuals, of confounding or anything like that, right? So even if we just stick to the purely pragmatic level, these things can actually lead to the fact that, Granger causality will not match causality. So takeaway message, Granger causality can match causality. It's a very practical tool, but it's not causality in the general case, as all of these examples show. And it also has none of these notions, which we arguably think that are causal and are useful, right? Just to give an example of this, actually. So imagine we have here just this observed bivariates time series, but it's actually trivariate. There is actually a hidden confounder here, Z, which is causing X and Y. Here again, we have these delays that we talked about earlier. So here's a delay of 1, here's a delay of 2. We observe only X and Y. And now we can, use faithfulness. Again, this is an assumption, but we could place this assumption. And then if we do deseparation, we see that Y will actually be dependent on X's past, given its own past. But it is going to be, X is actually going to be independent of Y's past, given its own past. So we are essentially concluding that X is causing Y, but not the other way around. So X is just causing Y. But this is obviously not correct, right? I mean, this hidden confounder, X and Y have nothing to do, right? They share the statistical information, but one is not the cause of the other and vice versa, right? So that's really, I guess a very cool highlight conceptually that Granger causality is not causality, right? You should rather think of it as forecasting, right? But there can be cases where it's causality, right? So there's still some kind of merit of calling Granger causality, right? I guess as long as you use Granger in front of causality, you'll always be safe. Huh? And yeah, so here we have another comic concluding this section. Actually, we are talking about terminologies. Well, I couldn't find a better one, but then, thinking about names, I felt like, okay, this might be a little bit funny as well. So we see a person, thinking to himself, oh, I hate when I don't know someone's name, but it's long enough, it's not awkward anymore if I ask, right? And then you see the full picture, right? And then, do you, Rachel, take this man? And it's a priest, they're getting married. And I said, aha, Rachel, he didn't even have to ask, right? So his wife-to-be now, he forgot the name, yeah. And I guess what I just want to highlight here is, before we already talked about how there can be different notation, right? And here there can even be different names to the whole framework, right? Like potential outcomes doesn't call itself causality outcomes or, true causal framework or anything, right? Perlian causality, on the other hand, yeah, it uses causality, right? But then again, we can justify why. But Granger causality, it's a different name, but there's no justification, right? And so I guess this is what I want to highlight here. So again, before moving on, any thoughts here, right? So we're doing a lot of jumps here. We are developing a lot of new ideas. So I guess this can be hard to digest, but anything you want to go back to ask questions about, or anything you're curious about more generally? Cool. If not, then I guess you're all very excited to. Oh, yeah, okay.
Getting pretty big.
Yeah.
So
The scaling thing again, yeah.
So is it really like, are they feasible when they're like choosing non-binary distributions for each of the variables in reality, or is it actually the goal to use the whole time series graph, or to reduce the time series graph to the summary graph?
That's an interesting question. I think I've seen both. Then again, as also Moritz will probably tell you, different level of abstractions, different levels of use, right? If I think, for example, again of the group in TU Berlin, then man, they're working with climate data and stuff like this, and that's not just big data. That's like data in the sense that it's like they have various features and whatnot, and overall kind of time steps. So it can be very big, but also it can be very noisy and messy, right? So, and they can actually handle stuff, right? They are able to make progress algorithmically and on the methodology side of things. So sure, I mean, it's a big thing, right? One of the key issues, right? And which is then again separate from causal inference, because it's not conceptually about how you do causal inference, but how you handle such a big thing, right? But some people do some amazing work there already, yes. Okay. So before the question came, what I want to say is I want to make the joke, right? That I'm going to tell you what causality actually is now, right? Like we have seen Granger causality, potential outcomes, Pearl causality, this causality, that causality. But Halpern actually knows what causality actually is, right? So yeah, Joseph Halpern from Cornell, he actually worked with Pearl. So it's not just him, also the famous, definitions of actual causality, there were the Halpern-Pearl, the HP definitions. But then again, he extended this work. He actually wrote a whole book on this topic. And it's very nice because conceptually you're doing very different things here now. And I actually, with my own research, resonate with these ideas a lot. I also got the chance to meet Halpern. He's a very nice guy. So yeah, the key distinction I want to highlight here, to maybe just put it in context to everything you have seen so far, type versus actual causality. So what is type causality? In your head, you can just think type causality equals to Pearl. Yeah? So it's all of these general statements, right? And by extension equals to potential outcomes. So, smoking causes illness, right? In general, right? Like if some, whoever it might be you hear about, you're, say, invariant to that, or you are naive or ignorant to that, that would be generally the statement you remember when talking about a situation like this. But in actual causality, we are concerned with particular events, right? Actual, right? Like that's I guess where the naming comes from, right? Because you're looking at particular instance, and you are not just saying like, oh yeah, smoking causes illness. I want to know about this particular case, right? Like what was here actually the cause, right? And so, it would be statements like this, the fact that David, whoever David is, no offense to any David here, but like smoked like the chimney for 30 years, right? And that caused him to get sick last year. So how can we, differentiate, general statements, average statements, random variable statements in a sense from like specific instances, right? So this really relates closely to this discussion that we have about ITE and ATE, right? Average treatment effect and individual treatment effect. And then again, given the nature of the individual treatment effect, the fact of fundamental problem of causal inference that you will never observe for any individual, both or or all of the counterfactuals or all of the potential outcomes, this, you know, you will realize becomes very challenging. Then again, actual causation is also studied, you know, through means of, you know, analytical philosophy, right? So it's really a philosophical topic, and however, it's analytical in its nature, right? We use formalism, we use logic to you know, capture these ideas, to pin them down, yeah. And so combined with what I just said previously, it's a really formal and technical and effortful endeavor. Now you might ask, right, just as a premise, so am I bad-mouthing this? No, not at all. I actually love this stuff, and I think also it's super useful, and not just me. Many people do that. For example, Tobias Gerstenberg in Stanford, he's a cognitive scientist actually working on causality, and he uses actual causality probably more than he does Perling causality. And why? Because they are very concerned with something like responsibility or blame, right? But also a thing like explanation. They can actually get meaning through the lens of actual causation. Whereas type causality is more this industrial way of thinking, right? It's more what a company would do. It's more what policy wants to do. It's prediction, right? Like, I know that, you know, smoking causes illness, right? So I pass a law that all smoking is, you know, prohibited, thus affecting the general health of the population, right? Sure, that might be immoral. That's a different thing, right? But that's what type causality could get you, right? But in actual causality, you're talking about responsibility, about blame, about explanation, about things that actually happen for a particular instance. So let's make this visual, right? It can be very daunting with all the text, with all the formulas. So this is also one which Toby would adapt. Balls, that could be billiard balls, right? Now we're just, you know, having some abstract balls moving in this 2D space. They're denoted A and B. Here on the right, this is the starting points. And they are traveling on this table. This is some surface. They can just travel. You can imagine how this would play out, right? There's some brick wall, and there's a goal. Goal as a hole, essentially, in this wall of the direction the balls are headed at. And now, you know, we can see, for example, that, you know, B could actually collide with A. And, you know, if A would collide with B, you know, the trajectory could change, right? This would be actually counterfactual, right? Because it would not be the trajectory it's actually taking. It's you know, or this one would be the counterfactual because you're saying B collided, and counter to the fact this would have been the case, right? And so let's make it a little bit interactive now. Maybe you've also seen this example or a very similar one in the motivation back then. But let's see scenario one here, right? We have this brick wall, we have A and B going according to these arrows. That's the trajectories. Did B hitting A cause A go into the goal? What do you say? Like, let's just raise hands for everyone who says yes. And everyone else who says no, I just assume they're saying no. Yeah. So you have to decide. Okay, we see the majority is saying that B hitting A caused A to go into goal. Yeah? Now I'm switching up things. What I'm changing now is I'm repositioning brick. I'm getting it out of the way. Yeah? But everything else has stayed the change, has stayed the same. So, and we asked the same question. What do you think now? So before everyone was saying yes. Do we stay with yes? Yeah, there's a couple of brave people who say it's still yes. Okay. So maybe explain me, what do you think? Why do you think? And by no means, this is like, don't feel embarrassed or anything, even if it turns out to be wrong. Right? There's no right or wrong here. No. This is just, yeah.
Maybe I would think about like if B is not with A, sure, it would still go to the goal, but that fact does not change the fact that B hitting A still caused it to go to the goal.
Yeah.
So it's a cause, but even if it wasn't there, it would still hit the goal, but that doesn't relate to the cause itself. Kind of.
I think this is perfectly sound and valid thinking. But as you would discover, you know, if you go down further this rabbit hole, right, you could construct examples, or depending on how you would set up this kind of definition, you would end up having troubles with other definitions. Mm-hmm. And what would happen, you would actually not get to the actual cause, right? So the intuition that the group here as total had was correct, that in scenario one, it's a yes, and in scenario two is a no. But then again, these are definitions, right? Like your definitions could be useful for something else, right? But then again, for the meaning of actual causation, it seems that we should stick to what the group was telling in scenario two and say no. So to just elaborate again once more. So since we imagine the counterfactual of B not hitting A, and thus latter hitting the brick, eventually failing to reach the goal. That's why we said it's a cause, right? Because A would have not went to the goal. Only when B occurred, right? It was necessary for B to occur such that it reaches the goal. So we say yes. But in the next case, right, it would have reached the goal regardless, right? So it's the other view of seeing it, right? But that's why we would say like, okay, because it would have not gone in, right? We would still have said, okay, it's not the cause, right? Because again, B is not necessary for A to go in there. Yes.
Okay, but then if you have this country, for example, the person is ill to the point where the person will die in like 2 days, and then the person gets hit by car and dies 1 day earlier, then would we say the car was not the cause of death because the person would have died anyway?
How was it here again? I think this is the Batman example that Halpan had. Do you remember, Tim, how this one was here? It's essentially like, because, you know,
I don't remember this example, but I would argue, at least for this specific death, it's still the cause, or the accident, or the car is still the cause. But maybe you find some description of a bigger picture where the car is not that responsible for much, yeah, or to play or make the death that bad. I don't know.
Yeah. So I guess everyone wants to jump in here, and that's actually cool. But in the interest of time, I wanna skip a greater discussion. But everyone, I believe, here is right in the sense that what we are doing here now collectively, or what we just started, was discussing what is the right definition, such that we capture a maximal amount of examples that we can come up with, right? So how can we find your example, the previous example, any other example we might imagine, such that our definition works on all of them, and does not work on the ones where we don't want them to work, right? Yeah.
So maybe just a short addition. There's a discussion about necessary causes, and then a gray field between sufficient causes. And I think this example might fit into this discussion, so that we can say, yeah, because the person is ill, it would be also sufficient for this person to die. So we have some shared responsibility, but nevertheless, the car has still responsibility for the death, because well, without the car at this place,
it would have happened later in time.
And if the person would not have the illness, then the car would be the sufficient cause.
Yeah. So in a sense, what Tim is now arguing is that there's shades of gray again, right? Like I was telling earlier in a different context, no black and white, right? You can actually have a continuous scale of like blame, responsibility, and stuff,
so
right?
This is the concept. So the frame allows for shared causes, not only a single effect or a single.
Okay, let's take a quick question here. Yeah.
Yeah, also we have to account for time, right? Because in your example, you have 2 days, and here we just looking at is the goal, and we goes the most into the goal, and not goes into the goal.
Yes.
After one period of time, that would be in the goal.
The good point here is that, obviously we're just talking in just natural language about these examples. But what he was just saying, if we specify the actual SCM, right, which then involves time or not, then there might be, even though they should represent the same example, the answers could, the conclusions could change, right? That's the point. It's a very good one. Okay, so what we just discussed is known as in law, or I know actually, I guess in US Supreme Court and these places apply this technique. It's called the but-for test. So it's a type of counterfactual reasoning, again, just like with the ball, because we were reasoning what would have had happened if A was not hit by B. That's a counterfactual, right? But it's counterfactual reasoning. We are running the simulation in our head to then, conclude our answer. And in the but-for test, you really just have this. You're just saying that A is a cause, a but-for cause of B, if but for A, B would not have happened, right? So again, in other words, B was necessary for A to occur. If B does not occur, A does not occur. Now you can actually express this more formally, right? And that's what I hinted at the beginning of this section, that, this can get very dense and very abstract easily, right? But, you're trying to abstract this concept. You're trying to capture it mathematically, right? We could have, for example, a grammar over, some events, phi. This could be just, some y equals y. It could be the negation. It could be some kind of Boolean combination in terms of conjunction, disjunction, right? And now we say that some, event xx is a but-for cause of this other event in a causal setting where M now is our regular SEM and U is a specific unit, right? If these two conditions hold. So first of all, our causal setting needs to imply our observation, right? So if we use the structural equation from our SEM, apply it to U, then we need to see X, right? But furthermore, it must be consistent with whatever we want to observe as the effect. And then here comes really the necessary part in, that there also exists an alternate state, which we could reach by intervention, in which our proposition does not hold. This is really just a formalization, and I don't want you to necessarily, comprehend all of this right now. But just, what I was saying is transcribed now here in this example, that, ball B hitting ball A could be modeled, for example, with x equals 1. We just have the symbol x representing whether, ball B hits ball A or not, right? And 1 is hitting. And then A reaching the goal could just be, our phi, which we just defined to be some, symbol y, which says y equals 1 if it reaches the goal. And then if B does not hit A, so you intervene, you just imagine you just take B away and let A, behave like it would normally behave, then it would not reach the goal, right? It would be y equals to 0. So what we can conclude, these two conditions hold. So ball B hitting ball A is a but-for cause of A reaching the goal. Now, as I was already hinting a little bit, and what this whole group was doing, which is super cool, is, to come up with ways of discussing the limitations, like which are the counterexamples where, this but-for cause breaks, right? And yeah, but-for is just, the basic thing we start with, and law employs it, but maybe they should not. Maybe they should result to something more specific. Then again, there's other issues because we typically don't have the SEM, right? So law cannot use, the SEM, right? But just discussing it on a philosophical note, we could construct an example like here in this box. Imagine now this scenario. You have two people, Susie and Billy. It's this famous example. And they both, pick up rocks, right? So Susie has one and Billy has one, and there's a bottle, right? And they play a game and they throw, right? And both of them are very accurate throwers, right? So both are capable of hitting the bottle right away if they throw it. But Susie's rock, because whatever, she was throwing faster, she goes first, whatever, hits first. Bottle shatters, right? Because the rock hits the glass of the bottle, the glass shatters. Well, because we know both of them are very precise, right? They would have hit anyway. Billy's would have also shattered, the bottle, had it not been for, Susie being faster, right? And here we actually can already see that, the but-for test would not work, right? Because the bottle would have shattered anyways. So Susie is not a but-for cause. It was not necessary for Susie to, shatter the bottle, because again, Billy's would have done that anyway. Similar also to your example now, right? But we still want to call it a cause, right? And so how did Halpern and collaborators and Sander Beckers and all these people, who work in this area go about it? Well, they defined what they then termed actual causation, right? And one of the definitions, this is the general, one of the first definitions, later on extended by the likes of Beckers. Looking like this, that, here I just took out the phi just to make it simple, just for the y equals y case. X equal to x, right? So the observation x, is an actual cause of y in our causal setting if the following three conditions now hold. Again, our causal setting can, generate these observations in the first place. But now there's these two vague, non-formal criterion, which are very formal, but it will be way too much here. Check out the book if you want to. But the second criterion is something that Tim was already hinting at, that essentially X is a necessary element of a sufficient set for Y. So there's a notion of a sufficient set for Y. There's a notion of a necessary element of a sufficient set, and that this actually holds for X and Y. And that X is minimal. So there can be no strict subset of X of, X could be multiple variables here, right? So this is just set notation here. I have not highlighted it in any way, right? But this could be, multiple things. And that thing is minimal. So there's no strict subset which would satisfy the second condition. And now if you would take any example and play through the formal game here with these conditions, right? When you also discover what they actually mean formally, then you would see that the examples would work. Like the example also, the previous one with Susie and Billy, right? We would actually conclude that Susie throwing was a cause of the bottle shattering, right? Which was not possible with the but for, right? So this is a conceptual achievement, a real development. And so this is also where, yeah.
Isn't Susie in this case not necessary? So
Exactly, she's not necessary. She's a
Yes.
but she's not a but for cause. But if you play here this game, Susie is a cause.
But she doesn't Susie throwing the rock not fulfill the second condition? Because her throwing the rock is not necessary for the bottle to shatter. So there is a set of actions that does not include Susie throwing the rock because her brother or her friend or whatever it is throws the rock anyways, where the bottle still shatters. So her throwing the rock, what am I missing?
Tim wants to tell you what you're missing.
I think to understand this example with this condition, we need to draw an SEM where we have some intermediate step. I think in the example it's them hitting the bottle in between, and then we have a layer with throwing, a layer with hitting, and have a layer with shattering. And now with this intermediate layer, we can think about minimal intervention and keeping it the same. So if we think about so in the actual setting, in the actual world, Susie is both throwing, but only Susie is hitting. So if we then also keep only Susie hitting, but if we keep then Bob not hitting and think about Susie not throwing, then the bottle would be not shattered. But it's all about constructing SEM and thinking about contrafactual words. You need to read this. Yeah, not as especially, but you have to extend the SEM.
No, in this case, you just need to read it from this because it's one sorry.
How was the structure? Was it, I think, some this or something like exactly something like this, right? And so you have Susie and Bob throwing, right? They both cause these one to hit, but Susie's cause whether Bob's hit or not because it's preemptive, and both of them affect essentially the shattering. They both could cause the shattering, right? And then you have the example from Tim, right? So essentially you have this triangular structure here, the confounder being Susie hitting first, and they, this hitting is both caused naturally by the throwing, right? You could even ignore that. You could just say it's confounder structure. You just need this connection here because you're making the statement about throwing, right? But then again, hitting is sufficient. Again, you will see if you play this through. I see that you're curious, and that's good. Just play it through, you'll realize, right? Again, that's why I was saying, right? Like, I'm not expecting anyone to right away understand this. Anyhow, it's not sufficient for you to actually understand now what's going on here, because this is just, it's even put in quotations because opposed to the third condition, the second condition is even more complex, right? And vague than the third one, right? But in essence, what happens is that, with this definition, Halpern and Pearl, they are able to overcome the limitation of the but for from before.
There's also a different view on this problematic if we don't want to extend the graph and think about responsibility, we could also think about, well, it's only necessary that at least one of them throw at the bottle. So, but both are throwing, and if just one would stop, it wouldn't change the results. So we have to make them both together responsible for shattering the bottle, and we can't say only one of them is responsible or both are independent of each other responsible for shattering the bottle. So this framework also in the book, Alban discusses also different approaches to problematics of non-necessary causes.
Why do Susie and shattering start this? I don't know. Anyhow, so thanks also for this awesome discussion. And I just want to conclude this section here with actually, I think this one was perfect, right? Like this is comic 1318, titled Actually, right? Which really just tells you that you can win every argument by just being one level more specific than the one before you, yeah? So for example, this person is saying, actually measurements suggest that our Earth is flat. Then actually it's a sphere. Then actually it's an oblate spheroid. And then actually I cannot read this. And then actually that's plus local topology and actually embedded in a universe that's curved, right? So you can always play this game, right? But we try to find out the truth eventually, right? And also the same goes for actual causality. And there's amazing, conceptual frontiers still to be discovered on this end, yeah? Okay, so with this, we have seen 3 different ways of causality, a non-graphical one called the potential outcomes, which however is super close to what we do anyhow with Perl. One framework which talks about time, which is not really causality, the Granger causality framework. It's more like forecasting, but still super useful and many people use it. And the third thing is actual causality, where we differentiate between, all these type causalities, which talk about, general effects and the actual instances. With this now, we actually have 10 minutes now to just talk, right? So with this, we have actually concluded part 1 now. Starting from the next lecture, we are gonna see more and more AI and machine learning related topics in the realm of causality. We are actually also gonna be on more dangerous frontiers because everything so far here had years and years to be developed, but the things we are discussing now next are things that have been developed in at most the last 10 years, not even that, right? So it's actually recent research, right? Recent science. So yeah, that's where we're gonna move. And you might not necessarily see directly the connection to AI or so, but then again, all of these works and everything that we deploy there and employ there are always with the hindsight, with the mind of AI. Even if they have to develop conceptually first, it's always with the goal of AI. So you'll also have these works. But now I really just want to take time to exchange, our thoughts. Again, not just questions, anything really. And I've put all these terms here because they help you remember all of these last 7 lectures now or so far. And you might see something like, oh, FCI, and then say, oh, what was this again? So you can ask all of these things, right? I will make sure to help you to get back quickly. Okay. Oh, yeah. So yeah, Moritz was asking whether all of these will be in the exam. Of course, yeah. No, but I mean, we'll try to be fair. It's just 3 credit points after all, right? And it should be about the learning. But then again, many of these terms are actually also very simple things, right? Like, for example, if we consider, Granger causality, it was just this one condition we saw today, yeah? Yeah, that's that.
The other concept of macroscience, first of all, is it like, can you simply say that we have a Macrobian SCM with all the exogenous variables at the end of the company?
Yes.
And what exactly is the Macrobian SCM ultimately allows to identify all?
Yes.
So, yeah.
You can also identify non-Macrobian, but it's not guaranteed for everyone, right? And then again, if you imagine just a confounder case, right? But the confounder is unobserved, and you cannot do anything, right?
That's a pretty strong assumption.
Macrobianity, Yeah. I'm also more on the side of calling most of the assumptions strong, even the standard ones, right? So I'd say yes, but people in the I guess in the broader sense of how people publish and everything, it's not a strong assumption.
So it's common to perform an SCMs but be able to model the system on such a degree that we have.
Yeah. Yes.
Can we do entity recognition?
Entity recognition.
So can we go ahead and claim for a certain amount of probability or security that the model should actually be appended, or maybe some nodes should be split to make the model simpler without reducing accuracy. So, for example, we have like one node in our model, which is wildly complicated, has a completely overfit probability function, but it makes stuff work. Can we go ahead and decompose this node into simpler nodes, so reduce entropy, so to say, without sacrificing accuracy? Is there a way we can say, okay, hold up, this doesn't make sense, this is way too complicated, this is actually 2 or 3 different things?
So I think your question is way too specific, which is why I'm going to answer a different one. Yeah, training for professorship. So my first counter to yours would be to say, okay, why was this complex, whatever that variable is, a variable in the first place, right? Like here, so far as you have seen classical pure causality, right? We are not concerned, like at most in causal discovery, we are concerned with learning, right? But even then, we know all the variables already, right? Like it's the features that we measure, right? We're just looking at the connections, right? And apart from that, right, we don't even have the problem. We are just talking about modeling assumptions, right? So all of these variables, they kind of make sense already. Then again, what you're actually asking is, okay, if I learned, just by some unstructured data which doesn't even have columns or whatever, right? Or maybe data which has, but it is some kind of abstraction, and so I need to cluster them, right? Some kind of, say, unsupervised learning, right? Self-supervised learning. Then that's the question of identifying a cause variable itself, or it's a question of cause representation learning, maybe, right? Which is then again part of abstraction and causal abstraction learning. And all of these things we have not discussed so far. Abstractions, I don't know whether we will actually cover in this course. Representation learning, I think we'll have a whole lecture on this, or at least, parts of it. So you see something there. But if we imagine now there, we learn something, and now we ask the question, can we split somehow to, still have the same model, but get maybe some better interpretability? I don't think I've seen any works doing that so far. However, I think that's super interesting. But then again, I think it's a very difficult problem. Yeah.
I maybe have a question about the prediction power, so to say.
I maybe have an answer.
And also regarding Simpson's paradox. So maybe if we imagine a statistician who's like doing some data work, and we're kind of discussing with him like how causal inference can be useful in the data analysis or something like this. Because in the Simpson's paradox, we argued that we can detect like the causal effect if we do calculus. But I was also wondering, like, if you there was also the assumption that we know all the variables that we need for the data analysis. But in the table that the statistician has, there are also all variables, and you could also detect like the thing with the kidney stones by just looking at the best fitting correlation, so to say, like the one with the highest prediction power, and you could also just use that. Like, how could you argue with this statistician that causal inference is like still better to do? Do you know what I mean?
Yeah. I think where you're pointing. Your question is about, like, okay, in the case where everything is observed and we can learn the perfect function, why do we need causality? The answer is very simple. It actually goes to these philosophical debates, which we also cover a little bit in the large-scale causality lecture, where one of our works, which was published this year, the Causal Parrots, it's discussing large language models. Because there's people also in large language models which make the claim now, oh, we have AGI, right? Sparks of AGI, of AI, right? And people even arguing, you know, if you have all the data in the world, it doesn't matter, we can just do correlation. Well, the reasoning is actually not wrong. It's sound. Like if you had all the data in the world and that's all there ever is, then you can do it. Then again, there's a huge flaw, which is you will never have all the data, right? And now the second flaw is, and that's the thing that applies also to your scenario, generalization. Like what if you have to move out, right? Like what if your distribution shifts? What if there's new data coming in, which you have not seen before? Then it doesn't work. Then it breaks down, right? Because correlation will not be stable of it. And that's really the simple thing. So as soon as you really want to be robust, it breaks down.
But if we
It's the difference between understanding and knowing, essentially. Yeah.
But if we observe new data, and I mean the new calculus predictions are also based on the previously observed data. So it also has just the information.
See, that's the thing. That's the thing. That's now okay. That's a different discussion now. This discussion now would be what Chris and we would also discuss in our group. How, you know, Pearl is protecting himself, right? Because Pearl is not making any claims of that sort, right? He's just saying, if that is the graph, yeah, then this is the right conclusion. And that's important and that's powerful, right? But now, whether this is true or not, right? Obviously, when you use the data, there can always be mistakes, right?
Yeah.
So that's why Pearl usually refers to himself as someone who provides a language to talk about these things, right? But obviously, we want to do all the steps at the same time, right? And then use, you know, data and just be data-driven and blah, blah, blah. And then we inherit all these problems, right? I mean, it's not like we are solving statistical inference with causality. Causality is a higher up problem, right? It subsumes statistical inference. So, yeah.
But still, like the distributions change, but the mechanisms, how they interact, if they are constant, then you are robust to that.
Yeah.
Only if the mechanisms would change, then you have a problem. But I think then basically no algorithm can help you.
Okay, and so we can think of like the power of inferences detecting these mechanisms.
Yeah. So it basically kind of solves this out of distribution problem that you commonly have in machine learning.
Yeah. Yeah, invariance of cause and mechanism, but also the principle of a mechanism, right? That it's something that is true, right? Like that there's some kind of absolute truth in that. And that's always powerful. Yeah. And yeah, very important questions. You're not the first to ask these. And yeah, it's just, that's the thing you have to challenge, right? But I think as soon as people understand this, then they are like, then it's funny because that's a very critical viewpoint, first of all. You're like, oh, this doesn't make sense, right? Does it, right? And then as soon as you realize this, you become like, oh, I actually have to do this. Like there's no other way around, actually, right? Like it's just you're jumping from one extreme to the other, which is super weird, but it's a phenomenon in this area. Anyone else? Everyone was smiling like, oh, it's time. Yeah, maybe one final one. Yeah. Of property.
Can we include generic properties in our models? For example, I have a bucket of water, and now that I kick the bucket, the water will flow out. I also have a bucket of oil, and without having seen it, by knowing that oil is liquid, I can also conclude that the oil bucket oil will also flow out.
A typing message, yeah. So there is actually so Moritz was already looking at me. I was like, I know what work to reference. So actually, yeah, there's one group from Canada. They worked on something they called typing assumptions, right? It's not you're in type causality, but typing assumptions are something different. What are typing assumptions? Essentially something like you just said, right? Like it's a liquid, right? And so I want to abuse the fact that I know both of them are liquid, or say, I don't know, there's different light bulbs, but I know they produce light or something, right? And you can actually use these kinds of assumptions if you know these things. For example, an expert could know, right? Like, oh, this is oil, this is also liquid, right? You don't need to be an expert for that, I guess, right? But still, you can have these assumptions, and then what it can do actually is restrict the Markov equivalence class when you learning these graphs, right? So you remember the Markov equivalence class, it's like all these graphs which could explain, which are very different in the terms of causality and where you conclude, oh, this is the cause of another, right? but all of them have the same, likelihood or whatever. And you use now these typing assumptions to reduce that space. In some cases, you can even get the unique graph just because of those, right? Yeah, so you can use that. And that's a very interesting idea. And I think you should keep up with these conceptual thoughts, because this is what gets a field advancing, I think, as well. Yeah, alongside, incremental and methodological improvement. Yeah. Yeah. Cool. Okay. I guess. Yeah. Okay. That last.
Something like hidden confounder detection, like in terms of significance level. Like
you want to do everything now, yeah? You want to get the holy grail. That's the thing, right? Like, how do we know what we don't know, right? Like, this is
just wondering if there's like a corresponding thing to like confidence intervals from statistics. Like we can say with 80% certainty that there is no.
Yeah. So I'm not aware much of discussions about, because it's causality actually, and then not, probabilities or properties of the data, right? And so I think that's a key challenge maybe in devising something like this, but we have thought about this, and I think you can actually make progress there. No one has done this so far as I know, but I think you can make progress by making some new conceptual assumptions on, say, the exogenous variable of an SEM, and suddenly conclude that, there must be this max amount of hidden confounders and this min or something, right? Like if you assume something about their functional properties or so. Of course, then you're saying like, how can you assume a functional property about a variable you don't know about? Fair point, yeah. But on a conceptual level, we got to make progress somewhere. Yeah? But that's at least an idea I also had. Yeah. Cool. Okay, then this was last. So this concludes part one, and the next one is gonna be part two. Yeah. So yeah. Yeah.